Hello everyone, to continue the chapter of steam turbine and major component fundamentals. In this video, we are going to discuss about steam turbine blading. Turbine blades convert the thermal energy of heat, pressure and velocity into mechanical energy, which is then supplied to the generator via the rotor. Each stage consists of stationary and rotating blades. There are basically two types of blade designs in use today, impulse and reaction. In the impulse design, theoretically all the pressure drop is across the stationary blading and essentially none across the rotating blades. This design is characterized by a long, slender rotor with diaphragms, which are used for sealing. In the reaction design, there is an equal pressure drop across both the stationary and rotating blades, which leads to very similar blade profiles. Reaction design is characterized by a drum-type rotor. Since there is a pressure drop across the rotating blades, a thrust is developed which must be compensated either by a dummy or balance piston or a modified steam path layout. Generally, the same blade profile is used for the entire turbine with the exception of the control stage and the last stages of the LP turbine. Blade heights vary to match steam conditions throughout the turbine. Both stationary and rotating blades are made from pieces of solid material. The rotating blade is an integral unit consisting of the root, blade profile and shroud. Ridges are machined into the outside diameter of the shroud, which is used to increase efficiency. Together with sharp-tipped, cocked and sealing strips on the casing, the ridges form a stepped labyrinth. Thus, small blade clearances are achieved without affecting reliable operation. Axial spaces between the strips and casing take into account relative expansion between the two components. All HP and IP rotating blades have rhombic roots which fit into circumferential grooves in the rotor. A complete blade row with no opening gates or special blades is obtained by inserting spacers between the blade roots and using a three-piece locking spacer to complete the row. A closed shroud ring is achieved by introducing a slight torsional pre-tensioning of the blades during assembly. Depending on the degree of stress, rotating blades have either 2 or 4 root serrations to transmit the centrifugal forces to the rotor. The stationary blades of the HP turbine also have rhombic roots, held in circumferential grooves by means of a shoulder on the inlet side. Depending on the design and application, some units are equipped with a control stage. To improve the partial load heat rate, the majority of turbines use nozzle control, that is, an impulse stage followed by reaction blading. The steam is expanded in one or more independent nozzle groups, each with its own inlet valve. The resulting expansion is transferred to the control wheel. In the ideal case with an infinite number of control valves, partial load throttle losses can be almost eliminated. In practice, most large turbines have 4 nozzle groups with corresponding control valves, and throttling takes place in the valve which is being opened. Generally, a steam turbine used in a combined cycle power plant does not have an impulse wheel because it is not load regulated. LP blading, which is a mixture of impulse and reaction blading, operates in a slightly different environment. Steam passing through this section on its way to the condenser expands from superheated steam to the point of saturation. This is where condensation of steam into water begins. Wet steam or droplets of water form, which can affect the blading. To prevent blading erosion, the leading edges of the blades are induction hardened. The long, last stage blades of condensing turbines are drop forged. Due to the length of this blading, additional stresses caused by centrifugal forces can occur. Therefore, the attachment of the blade to the rotor may be of rhombic or fir tree design. Stationary blades are held in place by blade carriers, attached to the turbine casing. The design of the unit determines the number of carriers. Attachment 2 shows the carriers used in your unit. The thermal masses of the carrier and rotor are matched, with the result that under transient conditions, startup and load changes, relative expansion is kept to a minimum. Radial adjustments can be made to the blade carriers in the HP casing. The turbine rotor and its blading are the principal and the most highly stressed components in the conversion of steam energy into mechanical energy. We use proven methods to supply the correct type of rotor for each application. On small to medium-sized units, the HP rotor is usually made from a monoblock. Rotors for larger turbines are made using a unique design and manufacturing method. They are made from welded discs. Slots are milled in the rotor, into which reaction blades are inserted. The coupling flange is an integral part of the rotor. Balancing holes permit the rotor to be balanced with the casing closed. That brings us to the end of this video today. In next video, we will be discussing about remaining major components of steam turbine. Thank you for your watching, hope you enjoy the lesson and see you then.